Everybody, I just want to take a couple minutes and explain Stan Meyer's frequency doubling effect. Now here I have my system all set up. I'm step charging to about 10 volts, a little less. I've got into the secondary circuit and into the cell 57 milliamps. Some gas production, not much, unfortunately. There's the chokes. There's the pulse transformer, diode, drive circuit. I've got 4 volts at 1.2 amps going into the primary coil. My gate frequency is 500 Hertz. And my drive frequency is 10 kilohertz at a 50% duty cycle, if you can see that. So back to the waveform. Here we're getting step charging, and I need to explain something before we get into this. When you put a pulse length of 10 kilohertz at 50% duty cycle into the system, that pulse length is equal to 20 kilohertz. I can show you that. So 20 kilohertz is the same as 10 kilohertz at a 50% duty cycle. So we'll spread this waveform out a little, get a better view of it. Take some measurements here. The start of the wave here is 2.12 milliseconds. There's our peak at 2.17 milliseconds. So subtract 2.17 from 2.12 milliseconds, so you get a pulse length of 50 microseconds, which is equal to 20 kilohertz. So a 10 kilohertz pulse at 50% duty cycle is the same as a 20 kilohertz at 100% duty cycle, as far as the pulse length is concerned. So now we know the distance from the start of the pulse to the peak is 10 kilohertz at 50% duty cycle, which is 5 microseconds. So now we look at the last half of the pulse, 2.17 milliseconds to 2.22 milliseconds. And subtract 2.22 from 2.17 milliseconds, and you also get a pulse length of 5 microseconds. So when we have the two together, we get 100 microseconds, which is equal to 10 kilohertz. Now 10 kilohertz, again, is 100 microseconds. And that is at 100% duty cycle. So when you get your pulse frequency doubling, I hope I'm explaining this right so everyone understands. All you're doing is you're converting the 10 kilohertz 50% duty cycle to a 10 kilohertz at 100% duty cycle. When your inductor discharges, it's filling in that last 50% of the waveform rather than just having it drop off and discharge the capacitor. So it's allowing you to have step charging when you get the pulse doubling effect, as you can see here. Now in this cell, in this circuit, I'm limited on my step charging. I can't seem to get anything over about 20 volts. And that goes back to the design of the coils. But once again, we are step charging to about 10 volts. 58 milliamps going into the cell. And our input of the primary coil is 4 volts at 1.3839 amps. Okay, now you can see what happens when the chokes are removed from the circuit. No step charging occurs, but what's interesting is we're getting much higher peaks in the capacitor. Peaks here are about 36 volts. but there's no step charging. Also note that our secondary circuit is pulling a lot more current to the cell, 162 milliamps. The gas production is increased. Notice the chokes are not connected, only the pulse transformer. People might ask, why do I have the chokes on a separate core? That's because I've never been able to get the pulse frequency doubling effect with the chokes on the same core as the pulse transformer. They're more likely to just act as secondary coils and not as chokes when they're on the same coil or the same core. So back to our circuit. Now we're still at 4 volts in the primary, but we're pulling 2.4 amps, a lot more current. So we know the chokes limit current anyways. This is just showing that. We're still at 500 hertz gate frequency and 10 kilohertz at 50% duty cycle drive frequency. So we'll go back and look at our waveforms and see what our pulse length is to see if we're getting frequency doubling without chokes. Just spread the wave out a little. Okay. This last portion here, this is the capacitor discharge, so it's not really part of the pulse going through the inductor. So we'll ignore that. Here our start, the start of the pulse is 1.11 milliseconds. And the peak is 1.16 milliseconds. So we'll go back, 1.16 minus 1.11. Once again, that's 50 microseconds. So we're back to a pulse length of 10 kilohertz at 50% duty cycle, which is equal to 20 kilohertz pulse length. So there you can see the difference between the two. Without chokes, you do not get the step charging effect, and you also don't get the frequency doubling effect, which is really the incorrect term. SAN calls it frequency doubling, which it does not do. It doubles the pulse length. It takes it from 50% duty cycle to 100% duty cycle. I hope I've explained this well enough for people to understand. If you have any questions, just send me an email or a message. Alright, thanks guys.